Hi everyone, in section 5.3 we are going to deal with some properties of integrals, which are kind of like properties of limits that we talked about first semester. So let's just begin. First of all, if you are integrating a function and your lower limit and your upper limit of integration are the same, you are basically going to find that the area of the rectangles adds up to 0. I'm sure you can draw yourself a picture of that and imagine that you are integrating from a to a, whatever those values are, f of x. It turns out, similar to the fact that area over the x-axis is considered positive and area under the x-axis is considered negative, when we switch the order of integration, it is going to be the opposite. So if we take the integral from a to b of f of x dx and we switch the limits of integration, it changes the sign of the result. A constant multiple. You can think of this as similar to a vertical stretch. So a vertical stretch is going to basically take the original integral from a to b of f of x dx and multiply it by what that stretch factor is, because you're only stretching it in one direction, which is effectively the same as pulling the constant outside of the integration. The sum and difference. If you are taking the integral of the sum of two functions or the difference of two functions, that is, you're adding or subtracting them first and then integrating them, it is the same as integrating them first and then adding or subtracting them. So you can split that if it makes things easier. So the integral of f of x dx plus or minus the integral from a to b of g of x dx. Also, if you're integrating a function, in this case f of x, from a to b and then from b to c, you can add those two together into a single integral and integrate from a to c of f of x dx. Or similarly, you could split that apart and integrate instead from a to c in one integral. You could split it apart into the integral from a to b and then add that to the integral from b to c. This is particularly helpful when you have geometric shapes. So let's say you are integrating a function that looks something like this and then like that. Okay, so a rectangle from a to b and a semicircle from b to c. Well, we can use geometry as long as we split it into two parts like that. This next property for integration is in the form of an inequality, and if we say max f is the maximum value the function f of x takes on the closed interval from a to b, and min f is the minimum value that the function takes on, what we can say is that if we were to take the minimum value of f and multiply it by the length of the interval b minus a, that is guaranteed to be less than or equal to the actual integral, which is guaranteed to be less than or equal to the maximum value of the function times the length of the interval. And to illustrate that, I'm going to show you with a little picture over here. We have this function, and we'll make this max f here, and we'll make min f here, and we'll go from a to b. So let's say we've got something like this, like that, okay? And so at A, in this case, we've got the minimum value, and at B, we've got the maximum value. We can have those occur at any place. But effectively what we're saying is, if we were to find the area of this rectangle, which is B minus A times min F, and the area of this rectangle, which is B minus A times the blue rectangle would extend all the way down to the x-axis, which is b minus a times max f. The actual integral of the function, which I'm going to shade here in black, would fall in between the values of those two areas of those two rectangles. In a similar way, if we have this relationship in number 7, where f of x is greater than or equal to g of x on a closed interval, then we can say that the integral from a to b of f of x dx is going to be greater than or equal to the integral from a to b of g of x dx. And again, we can illustrate that by just randomly graphing some function. So here's f of x, and we will graph g of x. F of x is greater than or equal to g of x. So there's g of x, and you could see clearly that the red area in this case is going to be, well, a to b here is going to be less than the corresponding black area under function f of x. So let's use these properties and do a few examples here. So we were given this information up at the top, and that I'm going to highlight in yellow, and we are asked to find the following integrals. The integral from 4 to 1 of f of x dx. Well, that is the opposite of the integral from 1 to 4 of f of x dx. So that would be the opposite of -2 or +2. The integral from -1 to +4 of f of x dx, well, I can see that that could be made up of the integral from -1 to 1 of f of x dx plus the integral from 1 to 4 of f of x dx, or 5 plus -2, which is 3. Here, you can think of this as using the addition rule and the multiplication rule, which is a vertical stretch. So we can write this as 2 times the integral from -1 to 1 of f of x dx, pull the 2 outside, plus 3 times the integral from -1 to 1 of h of x dx. And so that is going to be 2 times 5 plus 3 times 7, or 31. And the last one, the integral from 0 to 1 of f of x dx. Integral from 0 to 1. Now I think some people might have a tendency to say that would be half the integral from -1 to 1 of f of x dx. But you don't know that for sure. Okay? You don't know that there's that symmetry with respect to the y-axis. So this cannot be determined. And the last thing that we're going to do in this lesson is we're going to talk about the average value of a function. And the average value of a function, so let me graph a function for you. So let's say we've got this function here. We'll call it f of x, and we're going to go from a to b, and it goes something like that. Okay? And we are going to try and find the average value of that function. And by the average value, we mean the average y value. So let's kind of estimate where we think the average value to be here to get a visual of this. So right about there. And I am going to draw a horizontal line there. Actually, I'm going to draw that in a different color. I'm going to draw that in blue. And it turns out that if you were to form a rectangle, which its area can be found by taking the average value times the length of the interval b minus a, okay, turns out that that's actually equal to something. Well, it's a little bit hard to see, but if we were to integrate the function from a to b, what we would find is we would find this area right here that I am going to shade in blue, okay? And, oops, sorry, forgot to shade that part above the average value. And you can see if you take your rectangle, the portion where the function is below the average value, if you were to chop off this top part here, take that area right here and rearrange it, it would actually fill, so this area right here would fill these two areas here and here. So it turns out that the area of the blue rectangle is equal to the integral of the function from a to b of f of x dx. So those are equal to each other. Now, why is that important? Here's why that's important. Because if you want to find the average value of the function, you can take the integral from a to b of f of x dx and multiply it by or divide it by the length of the interval. Basically taking this right there, dividing both sides of that first equation by b minus a, the length of the interval. So ultimately, the average value of a function is the integral of the function over a specific interval divided by the length of that interval. So I'd like to do a few examples with that. The first one says use fn int. We're not going to do that because in the previous video we learned how to deal with this. So if you did a little bit of algebraic manipulation to figure this out, you would figure out that this function f of x is the top half of a circle going with a center at the origin with a radius of 3. So we have this is -3 and this is +3, and we want to find the average value of the function on the closed interval from 0 to 3. So we are going to find this area here, okay, and we happen to know that point right there is at a y value of 3. So we're going to find that area there from x equals 0 to x equals 3 and divide it by the length of the interval, which is 3. So average value of the function is equal to 1/3, or 1 over 3 minus 0, times the integral from 0 to 3 of f of x dx. Well, since we know the geometry here, it's 1/3 times 1/4 times pi times 3 squared, and let's do a little simplifying there. So what do we end up with? We end up with 9 over 12 pi, 9 over 12 pi, or that turns out to be 3/4 of pi. And if you take 3/4 of pi on your calculator, let's see, 0.75 times pi, turns out to be about 2.356. So what we're saying is that the average value of that function is approximately 2.356, which seems reasonable over that interval. All right, what I'd like you to do in this next one is take your calculator, pause the video, take your calculator, and find the average value of this function. Be careful, make sure you plug it in correctly, x sine x, on the interval from 1 to 6. When you're done, unpause the video and check your answer. All right, again, when you're using your calculator, make sure that you have it in radian mode. I would suggest in this case find the integral first and then divide that by 5, so you have 1/5 times approximately -6.342, and that's how you get that answer.